Okay, so today we will talk about another semiconductor device, the thyristors. So thyristors are, can be shown as a diode basically. So this is the symbol of a diode. But what we have as an extra is the gate signal. So they are controllable devices. We'll talk about that one. So they have the anode and cathode like in a diode. On top of that, we have a gate terminal. Okay, and if you would like to see what's inside a thyristor, a transistor can be an NPN or PNP junction, and a thyristor is PNPN junction, so it has like 4 layers. And actually you can make a thyristor yourself by just connecting one NPN and one PNP transistor like that, and the symbol you can see it. So what is the function of thyristor and how can it be used? Okay, so it is a diode. So you can have some current flowing in that direction, but you will not have no current in the opposite direction. But of course, in a normal diode, whenever it is forward biased, whenever you apply a positive voltage, the diode gets into the conduction mode, and it just carries some current through anode to cathode. But in the thyristor, you need to apply a gate signal like a pulse, so you can turn on the diode. Okay, so it is a diode that you can delay the on state. So what does it mean? So you can apply a positive voltage to here, but if you don't apply gate voltage, it will not start conducting. So it is like a switch, and the switch gets into the conduction mode whenever you apply a gate signal. But it is different from a transistor. So once it starts conducting, now it is basically like a diode, and even if you apply the gate signal or you cut off the gate signal, it will continue conducting as long as it is reverse bias. So it behaves like a diode, which you can delay the turn on state, but you don't have any control to turn off. So the only way to turn off a normal classical thyristor is to reverse bias it like a diode. Okay, so we don't have control while turning it off. So it can be in like different packaging. So it can be packed like in a normal transistor, one of the TO packs, or the higher current versions can be like that screw type ones. But actually thyristors can be used in like really large power applications. And this is a thyristor module, and actually it is not a single thyristor, but there are like 2 thyristors, and those are terminal 1, probably that one, terminal 2, and terminal 3 is the other one. But the tiny connectors through that one are the gate terminals for that thyristor. Okay, so in a thyristor controlled rectifier, we will see the thyristor topologies next week. But let's say you connect an AC voltage source, and you can have a RL load like a lamp or that kind of things, and actually thyristors can be used on that kind of dimmer switches that you can adjust the lighting. So if you have a circuit like that, so normally you have a waveform like that, and if it were just a diode, you will have like just the positive cycles like that. However, here it is your gate signal. If you just apply the gate signal at that instant, it will just start conducting like a diode. But if you somehow delay the gate signal, so here normally the device is like forward biased. Okay, so whenever the voltage is positive, it is forward biased, but it doesn't get into the conduction mode unless you apply a gate signal, and that moment you can start conducting. But then even if you cut off the gate signal, it will not turn off immediately. The only way to turn it off is reverse bias it, so it has to wait until the voltage or current will get into the negative region. And again, here in the last figure, the gate signal is more shifted, and from here to here, the idea, we will see those topologies next week, but you can have a voltage in that area. Here it is that area, so it is that area. So it just gives us some control over the output voltage magnitude and waveform. Anyway, we will see those things next week. And a thyristor, usually they have the highest current and voltage rating among other devices. So yes, we can use like MOSFET, which we will discuss in a couple of slides, and IGBTs and that kind of things. But thyristors usually have the highest voltage and current ratings among other devices. So they are kind of slow, compared to MOSFET. They are not suitable for switching at, kilohertz range or 100 kilohertz range. And it is a latching switch. So latching means you have control while turning it on, but you cannot have any control to turn it off. Of course, there are some specific thyristor types. This is just for the classical one. So there are a couple of VI characteristics. So that one, reverse blocking, is the same like as a diode. So it is the maximum amount of voltage magnitude that the thyristor can withstand without damaging. And apart from a diode, now we have the forward blocking. So you don't apply a gate signal and it will block the current. Then you increase the voltage, then it is forward bias, but as long as the gate signal is not applied, then it will not start conducting. So that is the maximum voltage in the positive direction that can withstand. And other one, like there are like three regions. You can think them like three regions. Like reverse blocking is when it is like that. You apply a positive signal, it is in the reverse blocking range, and the forward blocking, you can have the positive voltage like that, but gate current is 0, so it is blocking. And forward conducting is you have the positive voltage and you apply some gate current, so you trigger it, and if you trigger it, then among these three operating conditions, the only case that's conducting is the forward conducting range. So let's have a look at the VI characteristics. Okay, so here it is VI, just to remind, the normal diode, ideal diode, was something like that, right? And if it is a practical diode, it will be something like that. So you will have negative, when it's negative voltage, there will be no current, then it will be some forward voltage with the diode. So if your gate signal is high enough, so thyristor behaves like a diode. So you have the forward voltage and you have the reverse blocking voltage. But if your gate signal is 0, so there's no gate signal applied, yes, it will block the negative voltage like a diode, but it will also start blocking because you are applying some positive current, but you will not start conducting. Of course, there is like small leakage current, and if this is usually a high voltage, let's say 1000 volts. If you are beyond that voltage, then basically the thyristor cannot withstand the positive voltage, then it can start conducting. But if you are working somewhere in between, within the limits, so if you don't apply a gate signal, you will not conduct, and if you apply a gate signal, it will start conducting and behave like a diode. Okay, maybe that one is more clear. So here again we have the forward voltage. So if there is no gate voltage, it is still in the off stage and it is forward voltage blocking. That region is called forward voltage blocking, and this is the breakover voltage or forward voltage limit. And then that is the minimum amount of current. Okay, so there's that kind of nonlinear characteristics here. This is called the holding current, and holding current is the minimum amount of current that need to pass through the thyristor to get into the on stage. Okay, once it is at on stage, once you are here, so even if you cut off the gate signal, it will still keep conducting as long as it is forward biased. And in that range, whenever the voltage is negative, so applying a gate signal or not makes no difference. So in this region it behaves like a diode. Okay. So there are a couple of different types of thyristors, and in this course we are not getting into much details of that thing, but we will make a datasheet exercise and we can have a look at there. So SCR is the silicon controlled rectifier, so that's the most common one. There are like triac, diacs. I will show you the schematics, and there's also like a gate turn off thyristor. So this is an improvement, and this is usually used for like really high voltage and currents. This is a thyristor which you can turn off, apart different to classical silicon controlled rectifier type thyristor. Okay, so gate turn off thyristors, you know, the symbol is like that. So if you apply a positive gate signal, yes, you can enable those thyristors. But if you apply a negative gate current, it is also possible to turn off those thyristors. Okay. So GTOs or gate turn off thyristors are usually quite large. So here you see an example. So that one is, you know, one terminal which is just screwed, and the other terminal is below. So all that area is to used for carrying current, and for that specific type it was like 3000 amps at 4500 volts. So it is quite high, and you know, it's really difficult to find any other switches like MOSFETs or IGBTs working in this power range. So they are used at high power levels, and those two terminals here are for gate signals. So you can apply a positive gate current to enable this switch, and you can apply a negative gate current to disable the thyristor. Anyway, we will see the topologies next week. Okay, so GTOs are fully controllable, can be turned on and turned off, and turn on achieved by positive current pulse and turn off achieved by negative current pulse. So there's other thyristor type as the triac. So it's a bidirectional device, and triacs can be triggered by positive or negative current. Again, you know, triac is, you know, no different than two anti-parallel connecting thyristors. So the equivalent circuit is like that. You know, actually you can get a single thyristor. You can connect two of those like that. You can apply a negative signal. So the only advantage of that one in a normal thyristor, so the current can flow only in one direction, but here you can use that thyristor to carry current in that direction, and the other one can carry current in the opposite direction. So it is like a bidirectional current flow, and the equivalent circuit is like that. And you know, again, those things are quite commonly used in dimmers, you know, which you can adjust the intensity of light and that kind of simple applications. So let's make a datasheet exercise like we did with the diodes. So here we have a 50 amp 1200 volts automotive grade SCR silicon controlled rectifier thyristor. So okay, we have our datasheet. So this is for automotive applications, and again, you know, it's quite useful to read those descriptions. So it says again power supplies, solid state relays, motor drive applications, blah blah, and it can be used to switch like 8 amps for AC phasing and that kind of things. Okay, this is the package, and again you can see the symbol here, and blocking voltage is 1200 volts, blah blah blah. So let's have a look at, again, you know, the most important parameters are here. so the RMS current is like 50 amps, and the blocking voltage is 1200 volts, and this is I think repetitive voltage. This is non-repetitive, like single voltage. We will have a look at those things. And the gate current, in order to turn on that thyristor, your gate driver needs to supply 50 milliamps of current. So you turn on that thyristor by applying 50 milliamp through that gate terminal. And junction temperature, remember, I think the previous diode datasheet, it was like 175 Celsius. That model is more sensitive, so the maximum temperature allowed is 150 Celsius. So let's look at the other parameters. Again, this is like the normal current limit, but for non-repetitive, non-repetitive, so non-repetitive means you can survive a couple, maybe one or a few of those currents, but not in a repetitive fashion. Okay, so it can actually withstand up to 633 amps. Okay, almost like 10-12 times of the rated current, but the important thing is it needs to be like shorter than 8.3 milliseconds. Okay, and again, for repetitive off-state voltage, it can withstand up to 1200 volts. And another important thing, actually, we discussed it in the diode datasheet. The current is limited, okay, and also you will see some limits are di over dt, the time. This is current, and there is a like limit, how fast the current can increase. So you can still damage a device even if it is below the rated value, but if you just increase it too fast, like as a short circuit or something like that, then you will have some problems. Again, it is quite a high frequency. You can calculate it. 200 amps in 200 amps per microsecond is quite a steep increase. Okay, so the maximum, again, the minimum, I think it was 50 milliamps for the gate current, and it can withstand up to 8 amps from the gate terminals. Okay, and average gate power dissipation for the gate terminal, I think it just dissipates 1 watt. This is the storage. And let's look at the other parameters. Again, this is the required gate current. Like sometimes I think 10 milliamp is okay, but I think they are suggesting 50 milliamps. Okay, so again, this is the gate voltage and blah blah. Usually, thyristors are not voltage controlled, but they are current controlled devices. So your gate driver needs to supply the required current. Okay, and this is the latching current, and this is the holding current. So in order to keep the thyristors open, so you need to have like 100 milliamps already flowing through, not through the gate, but through the main terminals of the thyristor. Okay, so again, there are some other things maybe we should discuss later on this semester. And again, we will talk about the thermal design, but there's junction to case thermal resistance 0.3 Celsius per watt, and junction to ambient, so 50 Celsius per watt. Again, this is without any heatsink or so. So if you dissipate like 1 watts of energy, it will cause like 50 Celsius of temperature rise. And here, you can see like more detailed information about the power dissipation curves, average. Most of the time, the first couple of pages will be enough for choosing a device. But once you decided on your device, it will be helpful to look at all those graphs, so you can directly, for example, this is the holding and latching current with temperature. So depending on your operating conditions, you can check if your device will work as supposed or not. Anyway, again, this is a TO247 package. This is a common transistor package. Again, you can find all the information in this PCB design software and that kind of things. But if you need, there are all the dimensions that you require. Okay.